Next, we're going to talk about boundary conditions. In order to define a problem with a unique solution, you have to specify values of the dependent flow variables at the boundaries of the domain. In effect, you're specifying fluxes of mass, momentum, energy, and so on into the domain, and this is what drives the flow in the interior. Poorly defined boundary conditions can have a significant impact on your solution, and as you can probably guess from the red font, this impact is not a positive one. For this reason, as we move forward, we're going to talk not only about how to enter values in boundary condition panels, but also how to properly define boundary conditions and their locations. Defining boundary conditions requires three things. We have to identify what type of boundary it should be. For instance, is it an inlet boundary, a wall, a symmetry boundary, and so on. We have to identify where to locate the boundary, and we have to provide boundary condition data. The information that's required for the boundary condition data will depend on the type of the boundary, the location, and the physical models that we're using. The choices that we make when defining boundary conditions are going to depend on the geometry of the model, the availability of data, and also sometimes on other numerical considerations. This slide summarizes all of the different boundary condition types that are available in Fluent. Boundaries can be broadly classified as either external or internal boundaries. In the example that we see here, where there's flow through a pipe with an orifice in the center, the external boundaries include the inlet, the wall, and the outlet boundaries, and the internal boundaries are the orifice and also the orifice plate, which forms an internal wall boundary. Internally, Fluent splits walls such as this into a wall and a shadow wall, so here you see plate and plate shadow. This will be explained in more detail later on. External boundaries can be categorized based on the range of flows through which they can be used. So pressure inlet and pressure outlet boundaries can be used for any flows. Velocity inlet and outflow boundaries can be used for incompressible flows. And mass flow inlet and pressure far-field boundaries can be used for compressible flows. Other kinds of important external boundaries are walls, symmetry boundaries, axis boundaries, and periodic boundaries. And there's a few additional kinds of special boundary conditions to represent when you have vents or fans at the inlet and outlet of your domain. Interior and wall boundaries are the most common kinds of internal boundaries, but there's also so-called jump boundary conditions available, and this includes porous jump, radiator, and fan boundary conditions. The boundary condition types that you see here in blue font are going to be explained in more detail in the upcoming slides, and other boundary types may have descriptive material available in the appendix. Boundary zones and the boundary types are initially defined in the pre-processing phase, but it is possible to make changes to the boundary types after the mesh has been read into Fluent. In order to do this, you want to select the zone that you want to change in the list by left-clicking, and then simply select the new type of boundary from the drop-down list after you click on the arrow here. Entering boundary condition data is just like entering cell zone condition data. When you want to set the boundary conditions for a particular zone, you select boundary conditions in the problem setup tree, select the zone that you want to provide the data for, and click Edit. The Copy button, which you see here below the list of boundary zones, can be used to copy settings from one zone to another, and this can be a convenient feature for problems where there's a large number of boundaries with the same boundary conditions, and it can also copy data from one zone to multiple other zones. To specify non-uniform distributions of a variable at a boundary, user-defined functions or profiles can be used. Profiles can either be generated by writing a profile from the results of another CFD simulation, or creating an appropriately formatted text file with the boundary condition data. User-defined functions are explained in Level 12, and more details about how to set up and use profiles can be found in the appendix of this lecture.